Hiya! So in the last video, we talked about differential zero forms. And remember, these are just smooth real valued functions. And then another thing we also introduced were these things called elementary forms, which basically looks at the ith component in a vector. And these normally you would have thought, oh, this is just like some infinitesimally small thing. And we're saying, forget all of that. Forget everything you learned in calculus. Well, not everything. But forget that idea in calculus, and we're going to remap the way we think, and we're going to think about things differently. First, so in this video, we're gonna first talk about what a linear functional is. So what's a linear functional? So this is we've seen this word linear a million times. And so at this point, I kind of expect you to, well, have an intuition as to what this should be. And so this is just a function f that is a linear map. Right, so in other words, it's linear in some sense. That goes to R. So this is what a functional is telling us. It's telling us we're going to R. And in particular, all of these elementary forms that we saw before, they are linear functionals in our tangent space. And so are linear combinations of any of them. Well, since we have that, right? So since we have a linear functionals, etc., what we can do is just look at that. So we're going to use that, well, not precisely, but we're going to kind of use that to define a differential one form. So we let g1 to gn be smooth real valued functions. So remember, that is the same thing as saying that there's zero forms. Smooth real valued functions. This is the same as zero form, right? So these two are identical. And so we're going to get a one from our zero forms. And we're going to denote this by omega. And we're going to say omega is g1 of x1 up to xn. We took derivatives, right? So we have our forms here, our elementary forms. So we're going to put in our elementary form. So dx1. And we're going to do this for up to n. So x1 to xn, dxn. And this is going to give us a one form. And basically what it does is it associates to every point p to a linear functional on the p, right? So we're going from some point to a linear functional. So no longer to a vector, we're going to go to a linear functional on the tangent space. So in other words, what we're saying is that we're going to take a vector here. So the tangent space, we have a vector. And this is going to give us a linear functional. Now here, if we put v, what this little dash is saying is that's where the v goes. So in other words, this is going to send, oops, that is not an omega. This is going to send us to pv. And the way we define this, we just apply our omega. So we take this omega from above and we apply our point p to it. So in other words, what we have is we have g1 of p dx1, but we also still need to associate the v. So this v here, so here's the p. And the v here is going to give us the dx's. So this is the v. So this is a v of just v, I guess, yeah. And we do this for all of the things. g1 of p, gn, sorry, of p, dxn of v. And that gives us a linear functional. To make life easier or shorter, or not shorter, to make notation shorter, sometimes we're going to use omega p instead of omega p of something. But we have to remember that here we can apply, so like in this case, omega p of v, this is the same thing as saying omega p of v, right? So this is the same thing. Where are we in time? Yeah, okay. So let's look at an example. I'll give a remark and then we'll end the video. So let's look at this example. And we're going to consider the one form. So here I'm telling you what the one form is. I'm saying the one form is given by this linear functional. This function. And so if I have this function in A2, what we're going to first do is what is g1 and g2? So here g1 and g2, if we just look at our thing, right, this is just the coefficients. So here we have x and y. So g1 is x, g2 is y. Easy. Now what we're going to do is we're going to apply this point P to get a linear functional. So in other words, so remember how we were saying this and this are the same thing, so I don't really care which way we do it. We're going to write this out, and we go one step at a time. So G1 of P, so G1 of P we already said is X, right? So this is coming from here, G1 of P. And then the question is, what is this dx, right? So this dx here. So here we have dx of v. And what is that? We don't know for now. So what we're going to do is we're just going to leave it alone. This should not have a line under. Dx of v. And then plus, now at this point, you should see dy of v as well. So we have this. Now this x and y, we can apply this point P to it. In other words, this x really should just be 2 because we have a 2 in the x coordinate. And this y really should be 1. So here, I'll write this underneath instead. This is our x and this is our y. Because here, since we already have this P here, I should already have put the numbers in right away. Okay, so what is dx of v? Well, v, we don't really know what it is. That's a lie because I've told you what v is right here on the bottom. So v is some vector vx, vy. So remember what dx is doing. Dx is saying, give me the xth component. So in other words here, this is just going to be, where is it? I want this color. Vx is going to be this. So in other words, what we end up having is 2vx plus vy. And that's it. So this gives us precisely the linear functional. So as a quick little remark before we end this video, notice that just by comparing definitions, one forms and vector fields look very similar, right? So if we look at one form, so here on the bottom we have, or on here we have a one form, right, in 2.8. Here we have a one form. And we see it's G1 of D's, blah, 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 blah. And then if we look at a vector field, let's go all the way back and quickly look at a vector field. And if we look at a vector field, you'll notice how this is almost the same, but we have H1 and E1 instead of G1 and DX. So they look almost the same. And the thing is, something to note, very big thing, is that, well, there is a natural correspondence between them. And that is, oh, there's an error in my things, but this should be H1. Is this H? No, the other one's H. This is G. So G1 dx, 1, all the way up to Gn dxn. This you can associate to H1 E1, all the way up to Hn En. So there's a nice way to go from one to another. But like, as we've been talking about like very regularly, we have to remember that they are different objects. So the big thing is that we have to remember that these are two totally different things. So a vector field assigns to every point a vector of the tangent space. So a vector field gives us a vector, right? So a vector field gives us a vector. And a one form gives us a linear functional. Linear functional. So this is the kind of big things to note. So although they look the same, there's a nice way to go from one to the other. They are two totally different things. So we have to start remembering that they are different and to start separating them in our brain. And now, as in a little aside, vector fields and one forms are in fact what's called dual to one another. This is very similar to what's like row and column vectors. And like, we're not going to go into too much about duality, but here's a Wikipedia article on the side if you want to look at duality and like mathematics in general. But duality is a very important concept and it kind of appears everywhere. So we will end this video here. And in the next video, we're going to start looking at, well, these are called differential forms. So we're going to start looking at, well, differentiating. So I will see you in the next video. Peace.